In the early 1950s, inside the East Hartford, Connecticut factory of Pratt and Whitney, the ultimate American piston engine reached a dead end. The R4360 Wasp Major was an engineering leviathan. It featured 28 cylinders, 56 spark plugs, and displaced 4,160 cubic inches to produce over 3,000 horsepower. It was the largest, most complex, mass-produced piston aircraft engine in history. But on the hangar floor, mechanics covered in oil called it the corn cob, a maintenance burden that proved the internal combustion engine had finally hit its physical limit of heat, weight, and complexity. For decades, that massive radial architecture had been the undisputed symbol of American aviation strength. Now that exact mechanical mastery was becoming a trap, eclipsed by the high-altitude whine of the first jet turbines. But the real story of Pratt & Whitney is not only the story of the Wasp Major's collapse, it is the story of how an American factory taught the sky to roar, and what happened to the mechanics, the foundries, and the industry when that sound was forced to change forever. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place in Hartford, Connecticut in 1925. In 1925, American aviation was trapped by the weight of water. Following World War I, the United States Navy faced a severe mechanical crisis. Their airplanes relied heavily on liquid-cooled V-12 engines, primarily legacy designs derived from the Liberty engine. A liquid-cooled engine required a massive radiator, gallons of coolant, hoses, and water pumps. This plumbing added hundreds of pounds of dead weight to the aircraft. Worse, it was a profound liability. In a military context, a single bullet through a radiator hose would drain the coolant, causing the block, the main engine structure that holds the cylinders and major internal parts, to overheat and seize within minutes. On the freezing, wind-battered deck of a Navy ship, mechanics fought a constant battle against leaking pipes and cracked water jackets. America did not just need more horsepower, it needed a machine that could survive the brutal, corrosive, high-vibration environment of naval aviation without relying on water. Frederick Rentschler understood this vulnerability. Rentschler was a former executive at Wright Aeronautical, but he had grown frustrated with the industry's reluctance to push beyond existing limits. He believed the future belonged to the air-cooled Radial engine, a piston aircraft engine with cylinders arranged in a circle around the crankshaft. By placing the cylinders directly in the propeller's slipstream, the engine could cool itself using the rushing air, entirely eliminating the heavy, fragile radiator system. But to prove it, Rentschler needed money, engineering talent, and an empty factory. He found his opportunity in Hartford, Connecticut. Rentschler approached the Niles Bement Pond Company, a massive industrial machine tool manufacturer that owned an idle factory space previously used by the Pratt and Whitney Tool Company. Rentschler pitched them a bold idea. If they provided the funding and the manufacturing floor, he would build an aviation engine that would render the Navy's current fleet obsolete. In the summer of 1925, the Pratt and Whitney Aircraft Company was formed. Rentschler brought in brilliant engineers, including George Meade and Andy Wilgoose, and they set up shop in the Hartford plant with a single objective: design an air-cooled Radial that could produce 400 horsepower while weighing less than 650 pounds. The engineering team had to rethink how an American engine was put together. Older Radial designs suffered from weak crankcases that flexed under heavy loads, causing catastrophic internal failures. To solve this, the Hartford engineers did not just cast the crankcase, they forged it from aluminum in two solid pieces. They designed a master connecting rod, the central part that links the piston to the crankshaft, that was machined with unprecedented precision to handle the immense stress of high RPM operation. The resulting engine was designated the R1340, a number derived from its massive displacement. Displacement, the total volume swept by the pistons inside the cylinders, was exactly 1,344 cubic inches. They called it the Wasp. By late December 1925, just months after the company was formed, the first Wasp prototype was mounted on a test stand in the Hartford factory. When the engineers fired it up, the sound was deafening. It did not just meet Rentschler's promises, it shattered them. On its first major test run, the 9-cylinder Wasp produced an astonishing 410 horsepower. More importantly, it weighed only 650 pounds. This power-to-weight ratio was unprecedented in American manufacturing. In early 1926, the engine was shipped to the Navy for official trials. The naval inspectors were initially skeptical of air-cooled engines, assuming they would overheat under heavy continuous loads. But the Wasp survived the grueling 50-hour endurance test without a single failure. The Navy realized immediately that this engine changed the geometry of naval warfare. Without the weight of a radiator and liquid coolant, an airplane could carry more fuel, fly higher, and climb faster. For the mechanics working on the carrier decks, it meant an end to patching hoses in freezing saltwater spray. The Radial engine was accessible. A mechanic with a wrench could pull a single damaged cylinder head, the upper part of the engine that helps seal the cylinders and contains valves, without having to tear down the entire engine block. By the fall of 1926, the United States Navy placed an order for 200 Wasp engines. The Hartford factory floor exploded into motion. Pratt & Whitney had transformed from a speculative startup in an empty tool shed into a primary defense contractor in less than a year. Machinists who had spent their lives cutting steel for industrial tools were now shaping aluminum cooling fins and balancing heavy steel crankshafts, the rotating shafts that turned piston motion into rotational power. The air-cooled Radial had proven that an engine did not need to be heavy to be powerful. It just needed to be machined with enough precision to survive its own heat and vibration. But the Wasp did more than just solve a military logistics problem. The same qualities that made it attractive to the Navy, its durability, its lack of coolant leaks, and its low maintenance burden, caught the attention of a struggling civilian sector. In the late 1920s, American commercial aviation was a dangerous, unprofitable business. Airlines were using surplus military planes that were expensive to operate and terrifyingly unreliable. A commercial airline could not build a business model on an engine that required a complete overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards every 100 hours. They needed a machine that could fly day after day across deserts and mountains without seizing up mid-flight. The 410 horsepower Wasp had fundamentally changed what Americans expected from a piston engine. It had established the architecture of the air-cooled Radial, created a new industrial workforce in Connecticut, and convinced the military that liquid cooling was an unnecessary risk. The block was ready, the Navy was convinced, but the engine had not yet met the force that would turn it into an empire, the American commercial hangar. The United States Navy had proven that the air-cooled Radial engine would not overheat under military stress. But military contracts alone do not build an industrial empire. To permanently alter American manufacturing, Pratt & Whitney had to conquer a much more difficult environment, the commercial airline industry. In the early 1930s, American commercial aviation was a fragile, unprofitable experiment. Most airlines existed solely because of government airmail subsidies. Carrying human passengers was an afterthought, largely because the airplanes of the era were heavy, slow, and terrifyingly unreliable. A commercial fleet manager could not build a reliable schedule around a liquid-cooled engine that routinely blew radiator hoses or cracked water jackets over the Rocky Mountains. Furthermore, early aviation engines required a complete overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards every 50 to 100 hours. This meant an airplane spent nearly as much time inside a maintenance hangar, burning cash as it did in the sky generating revenue. The Pratt & Whitney Wasp changed the fundamental math of flight. By removing the liquid cooling system, the engine eliminated the most common points of mechanical failure. But the true breakthrough of the Radial architecture was how it was serviced on the ground. In a freezing hangar in Chicago, a mechanic working for a young Boeing air transport no longer had to pull a massive, monolithic V12 block out of an airplane's nose just to fix a single burnt exhaust valve. The Radial engine was inherently modular. A mechanic could stand directly in front of the aircraft, unbolt a single-cylinder head, lift it away from the crankcase, and replace it while the rest of the engine remained bolted to the firewall. This repairability came down to the internal geometry of the Radial design. Inside the crankcase, all the pistons had to connect to a single point on the crankshaft. Pratt and Whitney achieved this using a master rod, the main heavy-duty connecting rod that attaches directly to the rotating crankshaft, surrounded by articulated rods. Articulated rods are smaller connecting rods that pin directly into the sides of the master rod, rather than the crankshaft itself. This allowed 9 pistons to drive a single rotational point in perfect mechanical timing. For the mechanic on the floor, it meant an engine that was incredibly tough, tightly packaged, and completely accessible with a standard set of American wrenches. Because the Wasp was so reliable, overhaul intervals stretched from 100 hours to 300 and eventually past 500. The engine spent more time in the air. This mechanical reliability caught the attention of William Boeing, who realized that if he paired the Pratt & Whitney Wasp with a sleek, all-metal monoplane, he could revolutionize air travel. In 1933, the Boeing 247 took to the sky. Powered by 2 Wasp engines, it could cross the United States in 20 hours. It was the first modern airliner, but the American market immediately demanded more power, and a single-row radial engine could only grow so large before its massive cylinders created too much aerodynamic drag. The engineers in East Hartford realized they had to add cylinders without making the front of the engine wider. Their solution was the Twin Wasp, designated the R-1830. The Twin Wasp was a 2-row radial engine, a design where a second star of cylinders is bolted directly behind the first, slightly staggered so that the cooling air rushing past the front cylinders could still reach the cooling fins of the rear cylinders. It was a 14-cylinder machine, displacing 1,830 cubic inches, and it quickly pushed past 1,000 horsepower. The R-1830 became the turning point for American commercial aviation. It was this engine, alongside Wright Aeronautical's competing Cyclone, that powered the Douglas DC-3. The DC-3 was a machine that changed the geometry of the country. With 2 twin Wasps pulling it through the air, the DC-3 was fast, safe, and heavily capable. More importantly, it was the first airplane in history that could make a profit solely by carrying passengers, entirely independent of government mail contracts. The efficiency of the Pratt & Whitney blocks, combined with their low-maintenance downtime, allowed airlines like United Airlines and Transcontinental and Western Air to operate on fixed, dependable schedules. The sound of the radial engine was no longer just the sound of a military experiment. It became the sound of American commerce. In cities across the country, citizens learned to recognize the deep, rhythmic, thudding idle of a twin Wasp warming up on the tarmac. At the East Hartford factory, production lines expanded. Machinists were cutting cooling fins and balancing master rods in shifts, building a massive industrial supply chain that stretched from aluminum foundries to regional airport parts counters. The company had built a nationwide service network of mechanics who knew exactly how to listen to a Wasp, how to set its valve clearances, and how to trust its iron. By the late 1930s, the radial engine was the undisputed king of the American sky. Pratt & Whitney had proven that air-cooled power could make flight routine, profitable, and safe. The Wasp had conquered the commercial sky, but the factory in East Hartford was about to be asked to power something much darker, much heavier, and on a scale the world had never seen. By 1939, the Pratt & Whitney factory in East Hartford was no longer just building engines for airline schedules. The geopolitical map was fracturing, and the United States military realized that if war came, it would not be fought in the trenches. It would be fought in the stratosphere. To survive, America needed a piston engine that could pull heavy fighter aircraft into the sky at speeds and altitudes that were previously thought impossible for an air-cooled machine. The engineering answer was the R-2800 Double Wasp. The R-2800 was an 18-cylinder, 2-row radial engine, a massive, densely packed block displacing 2,804 cubic inches. When it was first run on the test stands, it produced 1,850 horsepower. Within a few years, engineers pushed it well past 2,000 horsepower. Eventually, with the addition of water injection, a system that sprayed a water-alcohol mixture into the cylinders to cool the intake charge and prevent detonation under heavy boost, it could produce an astonishing 2,400 horsepower in combat emergencies. This was no longer just a piece of machinery. In an America where an engine could decide whether a fighter returned to a carrier, a cargo plane crossed the Atlantic, or a commercial fleet stayed profitable, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. To meet the staggering demand of the United States Army Air Forces and the Navy, the East Hartford plant transformed into a city that never slept. The factory floor expanded across millions of square feet. The workforce swelled from a few thousand specialized machinists to tens of thousands of workers operating in continuous, relentless shifts. Because so many men had been drafted, thousands of women took over the lathes, the milling machines, and the assembly stations. They learned how to measure the tolerances of articulated rods down to the 10,000th of an inch. They learned how to install complex baffle systems, metal plates designed to force cooling air deep between the cylinder fins to prevent the rear row of cylinders from melting under the immense heat of combustion. The sound of East Hartford changed. The factory housed massive concrete test cells where newly assembled engines were bolted down, fired up, and run at maximum power to ensure they would not fail in the air. The deep, concussive thunder of 18-cylinder radials running at full throttle echoed across the Connecticut River day and night. It was the sound of a country brute forcing its way to air superiority through mass production. The R-2800 became the mechanical muscle behind the most decisive aircraft of the war. It was bolted to the front of the Vought F-4U Corsair, giving the bent-wing fighter the raw speed to dominate the Pacific. It powered the Grumman F-6F Hellcat, a rugged carrier-based fighter that mechanics loved because it could absorb heavy battle damage, lose a cylinder, and still limp back to the flight deck. In Europe, the Double Wasp powered the Republic P-47 Thunderbolt, a massive, heavily armored fighter that pilots affectionately called the Jug. The P-47 utilized a complex turbocharger system, a device driven by exhaust gases that forces more air into the engine, allowing the Double Wasp to maintain its 2,000 horsepower rating even at 30,000 feet, where the air was dangerously thin. But Pratt & Whitney could not build the R-2800 fast enough on their own. The government required them to share their blueprints with other American manufacturers to increase production volume. Soon, Ford Motor Company, Chevrolet, and Nash Kelvinator were all building Double Wasps under license. Automotive factory workers in Michigan and Wisconsin were suddenly building aircraft engines to strict Connecticut tolerances. The true test of the engine, however, was not just on the factory floor, but in the dirt of frontline airfields. On a coral airstrip in the Pacific, a mechanic did not have a clean, climate-controlled environment to rebuild a damaged cylinder head. They had a canvas tent, a toolbox, and a hoist. The R-2800 proved that American engineering had mastered the balance between extreme power and field repairability. A crew of young mechanics from farms in Iowa and garages in Ohio could pull a heavily damaged 18-cylinder engine off a Hellcat, swap in a crate replacement, reconnect the fuel lines and throttle linkages, and have the aircraft ready for a dawn patrol. The Radial engine had become the ultimate industrial weapon, and Pratt & Whitney was producing it on a scale that seemed impossible to stop. When the war ended in 1945, the military supply chain collapsed almost overnight, forcing massive layoffs across the American aviation industry. But Pratt & Whitney possessed an asset that guaranteed its survival: the absolute trust of the commercial airline fleet. The R-2800 Double Wasp did not retire with the fighter planes. It became the beating heart of post-war civilian air travel. Airlines like American, United, and Pan American rapidly expanded their fleets using pressurized, long-range airliners built around Pratt & Whitney engines. The Douglas DC-6, powered by 4 R-2800s, could fly above the weather, offering unprecedented passenger comfort. The Convair 240 series brought twin-engine radial reliability to shorter regional routes. By the late 1940s, the American commercial aviation network was entirely dependent on the ecosystem of the Radial engine. At major hubs like Idlewild Airport in New York or Burbank in California, the tarmac smelled permanently of 115-octane aviation gasoline and burned engine oil. Thousands of airline mechanics, many of them veterans who had learned their trade on coral airstrips during the war, formed a highly skilled labor force. They understood the nuances of carburetor icing, the mechanical rhythm of push rods, and exactly how much oil a healthy 18-cylinder block should leak onto the drip pans overnight. But the American market is never satisfied with existing speed or payload. Airlines wanted to cross the Atlantic Ocean non-stop, with heavier cabins, pressurized luxury, and massive cargo holds. To do that, they needed more than 2,000 horsepower per wing. They needed a piston engine that defied the limits of mechanical friction. Pratt & Whitney's answer was the R4360 Wasp Major, a machine that represented the absolute zenith of the internal combustion aircraft engine. The Wasp Major was a 28-cylinder, 4-row air-cooled radial engine. It was essentially 4 7-cylinder engines stacked back-to-back on a single massive crankshaft. To ensure that the cooling air rushing into the front of the cowling could actually reach the 4th row of cylinders, the cylinders were slightly offset, creating a spiral pattern. Mechanics took one look at this densely packed, highly complex structure and nicknamed it the corn cob. It displaced a staggering 4,160 cubic inches and generated between 3,000 and 4,300 horsepower, depending on the supercharger configuration. When it was mounted to the Boeing 377 Stratocruiser, a luxurious double-decker airliner that featured a lower-deck cocktail lounge, it represented the pinnacle of American industrial ambition. But it also represented a severe mechanical warning. The Wasp Major proved that the piston engine was hitting a thermodynamic and physical wall. In a commercial maintenance hangar, the R4360 was a terrifying proposition. A Boeing Stratocruiser required 4 of these engines. That meant a single airplane was powered by 112 cylinders, 224 valves, and 224 spark plugs. A routine pre-flight inspection required an army of mechanics climbing scaffolding to pull the cowlings, the removable metal panels covering the engine, just to check for fouled plugs or leaking oil lines. The sheer heat generated by 28 cylinders, firing in such tight proximity, was enormous. The rear rows of cylinders constantly threatened to overheat, leading to warped exhaust valves or catastrophic in-flight fires if the cowling flaps were not managed perfectly by the flight engineer. The engine consumed oil at a rate of several gallons per hour per engine, simply by design. It was a masterpiece of iron and aluminum, but it had become so complex that keeping it alive required nearly as much effort as building it in the first place. For airline executives, the Wasp Major exposed a harsh economic reality. An engine this complex meant airplanes spent more time in the hangar being wrenched on than in the air generating revenue. The cost of labor, replacement parts, and the massive volume of high-octane fuel required to feed 112 cylinders began to erode profit margins. The mechanical thunder was magnificent, but the business model behind it was straining under its own weight. The piston engine had reached the ultimate limit of horsepower, heat rejection, and human repairability. Pratt & Whitney had built the ultimate piston empire, but in the high-altitude testing grounds of their rivals, the air was already beginning to smell like jet fuel. The collapse of the American piston aviation empire did not begin with a bankruptcy or a catastrophic mechanical failure. It began with a quiet government directive, issued in the middle of World War II, that seemed at the time like a compliment. In 1943, the United States military recognized that Pratt & Whitney was the absolute master of the radial engine. Because the war effort required a constant, uninterrupted supply of R-2800 double Wasps to keep fighters in the air, the government explicitly ordered the company to halt all independent research into experimental propulsion. They were commanded to focus entirely on reciprocating piston engines. Meanwhile, classified contracts to develop a radically new technology based on British designs, were handed to industrial electric companies like General Electric and Westinghouse. At the time, the East Hartford engineers did not panic. They believed the piston engine would remain the dominant force in aviation for decades. But that government mandate was the first small crack in the foundation of the company. It effectively locked Pratt & Whitney out of the dawn of the jet age. When the war ended, the reality of that technological lockout became painfully clear. The British were already flying the Gloucester Meteor fighter with jet propulsion. General Electric was testing primitive but functional American jet engines. A jet engine, a turbine engine that produces thrust by accelerating air and exhaust gases, was fundamentally different from everything East Hartford had ever built. It did not rely on the violent, reciprocating massive pistons, connecting rods and valves. Instead, it used spinning turbine stages and continuous high-speed gas flow. Pratt and Whitney executives realized they were years behind their competitors. To buy themselves time, they pushed the piston engine to its absolute thermodynamic limit, resulting in the massive R4360 Wasp Major. But the Wasp Major inadvertently proved that the era of iron and aluminum pistons was over. In the late 1940s and early 1950s, the forces of the American market began to turn against the radial engine. The first force was manufacturing and operational cost. A commercial airline like Pan American could not afford the downtime required to keep 28 cylinders perfectly synchronized. In a civilian maintenance hangar, a mechanic was no longer just tightening bolts. They were fighting a losing battle against friction and heat. The Wasp Major burned massive quantities of oil by design. The sheer number of moving parts, hundreds of valves, push rods, rocker arms, and gears, meant that the probability of a mechanical failure increased exponentially. The second force was the physical limitation of the propeller itself. As airlines demanded faster speeds, the piston engine had to turn the propeller faster. But as the tips of a propeller blade approach the speed of sound, they lose aerodynamic efficiency and create violent shock waves. The piston engine had physically reached the end of the line. It could not pull an airplane any faster, no matter how much displacement the engineers in Connecticut added to the block. Faced with the terrifying prospect of becoming obsolete, Pratt and Whitney initiated a desperate internal crash program. They poured their massive wartime profits into the development of a turbine engine that could leapfrog General Electric. The result was the J57 turbojet, an engine that utilized a dual compressor design, allowing it to compress incoming air much more efficiently than early single-spool jets. The J57 was an engineering triumph. When it was mounted on the Boeing B-52 bomber and later adapted into the JT-3C for the Boeing 707 airliner, it revolutionized global travel. Pratt & Whitney had successfully secured their future in the new era of aviation. The company would survive. But the survival of the corporate badge did not mean the survival of the old industrial culture. The shift from the R4360 piston engine to the J57 jet engine triggered a brutal, systemic transformation in how American power was manufactured and maintained. Inside the East Hartford factory, the entire nature of the work changed. For a quarter of a century, the floor had been dominated by the heavy machining of steel and the casting of aluminum cooling fins. Machinists measured their worth by how perfectly they could balance a heavy, forged crankshaft. The jet engine required entirely different materials. It required titanium, exotic alloys, and sheet metal fabrication that could withstand continuous internal temperatures that would melt a piston block. The heavy foundries were slowly phased out. The rhythm of the factory line, once defined by the assembly of heavily bolted iron blocks, transitioned into the sterile, high-precision assembly of delicate compressor blades. The company had saved itself, but the transition would exact a brutal toll on the foundries, the mechanics, and the sound of the American aviation industry. In October 1958, a Pan American World Airways Boeing 707 took off from New York, bound for Paris. It was powered by 4 Pratt & Whitney JT-3C turbojets. On that day, the piston engine empire was fundamentally broken. The jet did not just fly faster and higher. It broke the economic model that had defined American aviation for 3 decades. A turbine engine operates with continuous combustion and perfectly balanced rotating assemblies, rather than the violent, reciprocating, stop-and-start motion of thousands of heavy metal parts. Because it had a fraction of the moving pieces, a jet engine could stay bolted to the wing of an airliner for thousands of hours without needing a major overhaul. It did not foul spark plugs. It did not snap push rods. It did not leak gallons of oil onto the tarmac overnight. Furthermore, the jet engine ran on Jet a kerosene-based fuel that was significantly cheaper and easier to refine than the highly volatile, heavily leaded 115-octane aviation gasoline required to keep a Wasp Major from detonating itself to pieces. The airlines looked at the fuel costs, the maintenance downtime, and the sheer speed of the jet, and immediately began canceling their piston aircraft orders. This commercial shift triggered a massive collapse in the American aviation service network. For a generation, an airline mechanic was a master of mechanical intuition. A skilled mechanic working on the ramp at LaGuardia or Chicago Midway could stand next to an idling R2800 double wasp, listen to the rhythm of the exhaust, and know exactly which valve was sticking just by the sound. They could diagnose a failing carburetor, a device that mixes fuel and air before the mixture enters the engine, by the smell of the exhaust. They fixed problems with wrenches, feeler gauges, and physical leverage. The turbine engine silenced that culture. A jet was not diagnosed by ear, it was diagnosed by instruments, thrust pressure ratios, and eventually computers. It was a sealed cylinder of high-speed gas flow. When a jet engine required an overhaul, a mechanic on the tarmac did not tear it down to replace a single compressor blade. The entire engine was unbolted as a single modular unit, shipped to a specialized, sterile facility, and replaced with a fresh pod. The tactile wrench-turning art of the flight line mechanic was replaced by the clean room precision of the aerospace technician. The physical landscape of American aviation changed rapidly. In the early 1960s, massive, perfectly functional piston-powered airliners, DC-6s, DC-7s, and Boeing Stratocruisers, were flown to salvage yards in the desert Southwest and parked permanently. The market had moved so fast that airplanes with years of structural life left were suddenly worthless. The magnificent R-4060 Wasp Major, the most complex piston engine America ever built, was suddenly being stripped off wings and sold for the scrap value of its aluminum block. At the factory in East Hartford, the transition was permanent. Pratt & Whitney expanded into a massive corporate entity, eventually becoming a cornerstone of United Technologies. They dominated the military and commercial jet engine markets, building the power plants for the F-15 fighter and the Boeing 747. The badge remained one of the most powerful symbols in global aerospace, but the piston engine division was quietly, systematically dismantled. The company that had built its name on air-cooled radial engines stopped developing them entirely. The production lines that had once cut the steel for master rods and cast the aluminum for cylinder heads were reconfigured for titanium and superalloys. The men and women who had spent decades learning how to balance a heavy steel crankshaft found that their specific mechanical mastery was no longer needed. The company was no longer building iron engines that could be repaired. It was building thermodynamic flow systems that were sealed. By the late 1960s, the deep, thudding idol of the radial engine had vanished from major American commercial airports. The network of parts suppliers, the specialized tooling, and the mechanics who knew how to keep them running were scattered. What had once been the defining sound of American industrial power had been replaced by a high-pitched, efficient whine. The piston had lost to the turbine. The engine still ran. The orders stopped. The fuel changed. The foundries closed. The wrenches were put away. The turbine took the sky. The badge survived on the cowling. The mechanical thunder was gone. Pratt & Whitney survived the jet age, but the iron empire they left behind would only speak again in the places where time had stopped. Today, the Pratt & Whitney badge remains one of the most dominant symbols in global aerospace. The company did not fail. It successfully navigated the most dangerous technological transition in industrial history. Today, as a massive corporate division, Pratt & Whitney builds the F-135 turbine engine that powers the military's F-35 fighter, and they produce the geared turbofans that move thousands of commercial airliners across the globe every single day. The company is a titan of high-speed gas flow, software diagnostics, and exotic metallurgy. But the piston aviation empire, the industrial culture of heavy iron, air-cooled cylinders, and wrench-turning repairability, is entirely dead. The original East Hartford factory complex still exists, but the massive foundries that once cast aluminum cooling fins by the millions are gone. The concrete test cells that once shook the Connecticut River with the thunder of 28-cylinder radial engines have been dismantled, replaced by sterile testing facilities designed to measure turbine bypass ratios and digital sensor telemetry. Yet the engines they left behind refuse to vanish entirely. The Pratt & Whitney radial engine survives today in a fractured, highly specialized afterlife. The most extreme example is not found in a museum, but in the brutal, freezing environment of the Alaskan wilderness. In places where modern infrastructure ends, the piston engine still holds a strange economic advantage over the turbine. Operators like Everett's Air Cargo still fly vintage Douglas DC-6 airliners, powered by four R2800 double WASP engines, into remote, unpaved gravel airstrips. This is not a gimmick. It is a strict calculation based on the physical realities of the American engine market. A modern turbine engine is incredibly reliable in clean air, but if it ingests a load of coarse gravel on a backcountry runway, the delicate compressor blades shatter, resulting in an overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards that can cost millions of dollars. An R2800 radial engine, however, can swallow dust and gravel, vibrate violently, and keep running. If a cylinder fails in the freezing Alaskan wind, a mechanic can park the airplane on a frozen lake, unbolt the damaged cylinder head, swap it out using standard hand tools, and fly the airplane back to civilization. For a dedicated community of preservationists, restorers, and vintage mechanics across the lower 48 states, these engines are not just historical artifacts. They are the ultimate expression of American mechanical transparency. Every summer at the Experimental Aircraft Association's AirVenture Fly-In at Oshkosh, Wisconsin, the sky fills with the deep, concussive thunder of preserved Corsair and Hellcat fighters. The men and women who keep these warbirds flying do not plug a laptop into a diagnostic port to see what is wrong with the airplane. They read original, oil-stained service manuals. They measure valve lash with steel feeler gauges. They hunt for new old stock gaskets in parts bins at aviation swap meets. They machine their own replacement parts when the original supply chain fails, knowing that when the last forged master rod is broken, it will cost a fortune to cast a new one. There is even a strange, violent footnote to the ultimate dead-end engine, the massive R4360 WASP Major. Long after the commercial airlines scrapped them, these 28-cylinder behemoths found a second life in unlimited air racing at the Reno Air Races, and incredibly in extreme tractor pulling competitions. Stripped of their commercial weight and pushed to the absolute breaking point with modern fuels, they proved that the Hartford engineers had built an engine block capable of producing nearly 5,000 horsepower, even if it was ultimately too expensive for an airline fleet to maintain. This preservation is not merely nostalgia. It is a physical argument about how America used to define power. A modern jet engine is an undeniable miracle of efficiency and safety, but it is fundamentally closed off from human intuition. It is a sealed thermodynamic system. The air-cooled radial engine was different. It was a machine that could be understood simply by looking at it. A mechanic could trace the path of the fuel from the carburetor to the intake valve, watch the push rods actuate, and feel the exact moment the spark ignited the cylinder. It required human labor, physical leverage, and a deep tactile relationship between the machine and the operator. When the commercial market abandoned the piston engine, America gained altitude, speed, and scheduling reliability, but it lost a massive industrial service network that relied on physical intuition. The world of the flight line mechanic, covered in oil and wrestling with a master rod, was replaced by the clean, software-driven reality of modern aerospace. The sound of American air power shifted from a chest-rattling roar to a high-pitched, distant whine. Somewhere in an American aviation museum, an old R2800 double WASP sits on a metal drip pan under warm lights. The deep aluminum cooling fins are dusty. The massive steel cylinders are silent. But if you stand close enough to the crankcase, the metal still holds the faint, unmistakable scent of heavy engine oil and high-octane aviation gasoline, the lingering ghost of a mechanical sky that no longer exists. See you in the next one.